Yeah, go ahead.
Um, Hi. So, good morning. So today I'm going to introduce a paper, deterministic streaming sketch for rigid regression. So this is a paper is published as AI Stat 2021 last year by Jeff and his student Shiben Wei.
Why we don't ask Benwei to present?
Yeah, I think we maybe it's a better option. So I think for me, I also learn from this paper. As I would like to use this method in my own project. Okay, so firstly, I would like to talk about the background. Why I would like to borrow some idea from that paper. So as you know, I'm working on the network pruning project, and one of the very efficient method in the pruning method is the gradient-based pruning. So as actually, I have introduced the gradient-based pruning in last semester. So today I will going to have a very brief introduction of that method. In this method, is trying to minimize the loss before the difference of the loss before and after pruning. The way it to approximate the difference is by Taylor expansion. So in that Taylor expansion, it depends. So we have a delta L is equal to delta W transpose multiply Hessian multiply delta W. Delta W actually that's the change of the weight. In its solution, there is a term that's the Hessian inverse. So for all the method based on the gradient, it always need to calculate the Hessian inverse. But as we know, the time complexity to calculate the Hessian inverse is the cubic of D. D is the number of the weight in a neural network. So that would be too time consuming.
I have a question about the objective. Why the target DLBR function is to minimize the loss difference? Because a trivial solution will be sigma is equal to 0 here, right? So I thought that network pruning should be it should be minimize the difference between the performance before prune and after pruning, and also some score function about the number of parameters. But simply minimize the difference will give you a trivial solution.
Yes. So actually, in this equation, we didn't give out the constraint about the number of the remaining weights. So in general, so if there is a target pruning ratio, so we need to have a constraint at delta W. So for some weight Wi, its delta W is equal to minus Wi. So that's the constraint I haven't put on this slide. So yeah.
Yeah. Okay. Never mind. I just I got the idea. Thank you.
Okay. So.
Could you go back to the previous slide?
Sorry.
I have a question. Could you go back to okay? In the approximate object function, the first equation, we ignore the second term because of the gradient is 0. Is that the meaning of it?
Yes. Actually, yeah. So firstly, this pruning method is on a well-trained model. So we assume the first order gradient is close to 0. But as we know, it's impossible to make the gradient to be 0. But in practice, actually, I also don't know why. I mean, when I did the experiments, I tried to include the first term of the gradient. The result become the performance dropped dramatically after I add the first term gradient. Empirically, the first order gradient cannot be 0. But in practice, if I have the first order gradient, the performance with this method would be too bad.
Then what's the reason or rationale that we can simply ignore or discard this term?
Honestly speaking, I don't know why.
So is it like on average, this one will be significantly less than this third term?
Actually, is larger. If I have the first order gradient term, the value would be much larger than the second order gradient, and it would be dominate in the delta L, and will lead to bad performance. I know there is also some method. It also use this Taylor series to as the objective function of the pruning. So for some method, it just use the first. It only use the first term, first order gradient, but that performance is even worse than magnitude-based pruning.
Do they explain why, like in theory, you shouldn't ignore the term, and in practice, it's much larger than the third term? Then why the Combs algorithm normally ignore this term and they works better?
So I feel actually it's the opposite. In theory, we assume because a model is trained very well. So if it's on a very simple data set like the MNIST, after training, the performance is always go to 99 point something percentage. That's the test accuracy. So it always assume the lambda L, the first order gradient, is close to 0.
Okay, so it's on theory, when the model converges, this gradient will be nearly 0. So we can
yes.
ignore it and derive whatever follows.
Yes. Okay. But I would like to say, in practice, actually, it's hard to go to 0. I mean, the magnitude of the value in the first order gradient is still greater than the Hessian. But if I use the first order gradient in the objective function, the performance is worse than just use the second order gradient.
Did you use SGD or use default gradient?
Use the SGD.
In SGD, it's never 0. That's for sure.
Yes, sure.
So if you use the full data set, will it be 0?
What data set? Sorry.
The full gradient.
Full gradient. So what's the full?
In theory.
You mean
the problem is here. So we know that when you add the first order term, you should be able to give a better approximation. However, when she did consider this and put it into a network pruning project, and performance drops dramatically. And that's the reason. We don't know why.
Yeah,
and,
I mean,
even worse, like because Hessian matrix is very huge, right? You have to introduce some like a block diagonal approximation. We found that block diagonal approximation is even better than full Hessian. So there's some problem with this crude approximation with Taylor expansion.
So if we consider the full gradients, then if you as the model converges, the gradient should be 0. But if it's in the case of SGDs, then the second order, the first order will never be 0.
It's not 0.
So,
but if you consider the influence of the first order term, it doesn't give you a good pruning result.
Yeah, so actually till now I haven't found any explanation why the first order gradient doesn't work as well as the Hessian in the pruning problem. So as we just introduced, we need to calculate the Hessian inverse, and we know that it will spend in general it will spend all the cubic to calculate the Hessian inverse, and another thing we need introduced by another paper, the Wood-Fisher paper, is that it tries to estimate the Hessian matrix with the Fisher matrix. So that is actually it gets the empirical Hessian matrix by the gradient transpose multiply the gradient, and with this method, we need to calculate the multiplication of G transpose and G, and then calculate its inverse. So this is still very time consuming. so today I'm going to talk about the Shiben Wei's paper. In its paper, it proposed a method, a streaming method to calculate the inverse matrix efficiently. So firstly, I would like to introduce the problem statement in this paper. Firstly, it tries to solve the rigid regression problem. For the rigid regression problem, is that given a matrix, its dimension is n by d, and it tries to solve the problem ax is equal to b, and it tries to get the solution of x. So in the regression problem, it's trying to minimize ax minus b, the mean square error. And in the rigid regression, it introduced a regularization term here, and the coefficient is gamma. So actually to solve this problem, we can say that it's the derivative to be 0, and with that we can get the x gamma is equal to this formulation. In this formulation, we can say that there is a term a transport multiply a, and another term is a transport multiply b. So for those two terms, the space for them is OD square and OD, and the time complexity is OD cubic and m minus d square. Yeah. Is there any problem here about the time and the space? Okay. So in general, to calculate this solution efficiently, one way is that possible for us to approximate the matrix A in with a smaller matrix. So currently, the dimension of the matrix A is n by d, and we assume n is much greater than d. So as we know, if we use the compute the SVD of A and then approximate it with the first k singular vector x, then we can get the ax. The spectral norm is greater than t. So with this one, it's possible to represent the matrix A with only k singular vector and the corresponding singular value. So then assume then the space for A would be k by d, and it will also become faster to calculate those two terms in the objective in the solution.
Could you? So what's the problems here? Like what are they trying to do? What's the problem with this solution? Time complexity or space complexity? What's the limitation or constraint they want to solve?
Yeah, so in Shipman's paper, it tries to propose a streaming method to calculate the solution efficiently. So currently, if we need to, so the problem is that the time and the space is too large. So
which one is too large?
Both the time and the space. So for the time, for the space, after we calculate a transpose multiply a, the space would be d squared, right?
So if you assume m is much larger than d, then I don't see why do
yeah.
here.
Yeah, sure. So then that space is O and D. I mean, it's also very large, and the time for the time is, I mean, it's even in cubic. So assume, let's say D is equal to 1 million. For example, in our network pruning, there is 1 million parameter. Then the time and the space would be too large.
Then what's your n?
Yeah. So in Shipman's paper, they propose a streaming method. So every time they just need to look at a block of the A, and then use that block of A to approximate the original matrix.
So in their problem, so D is much larger, so they need to calculate it efficiently, right? If D is very small, why do we care about like efficiency? If you have 10 features or 100 features, then it's totally okay.
Yeah, you are right. So D is very large. So I checked their experiments. So there is always like the millions of I mean, D is in million.
Okay, so you say M is much larger than D is quite misleading. I thought D is small and M is large, so I couldn't think about what they're trying to do.
Yeah, both are large, and the D and the N can be much larger. So it means that you can, even N can be infinite. You can have I mean, with the streaming method, you can have as much data as you want, and we always expect that with more data we can get better performance. We can, yeah. So the problem here is that how to estimate A efficiently, and one way we can think about is that we can use the SVD, calculate the SVD of the matrix, and then we just use the first k singular vector and its corresponding singular value. But when the matrix A dimension is pretty large, SVD is also time consuming, right? So in this paper, it proposed a streaming way to for all this method for this problem. So before we go to detail of that algorithm, I would like to introduce the frequent atom algorithm first to have intuition about the frequent direction method in the paper. So for the frequent atom paper, it first proposed in 2003. So assume we have a stream from A1 to AN, the capital A1 and AN, and actually there is only a different term in this stream, but M is still large. So assume we have 100 different atom, then M is equal to 100. But we only have like the 10 budget. Then what can we do? So for the frequent atom, when we try to calculate the frequency for each atom AI, let's say that's the Fi. The frequency would be the how many times the AI appear in the stream. So in this method, it's trying to approximate the frequency Gi. So it can have the Fi minus Gi will be smaller than N divided L, and the L is a budget. So we can check. Sorry. Okay, so what it did is that given the streaming for okay, so in this algorithm, the input sequence is indicated by x1 from x1 to xn, and k is the budget, and assume we for each so there is a count array, and for that count array, it will record the counting of a certain atom. So when a new atom comes, it will add one more counting for that atom, and after it will try to subtract the counting empirically.
I think you go to the details too quick. So what are they trying to do here? Could you explain in a high level?
Yeah. So firstly, this is a problem trying to count atom in a very large array, or in a very long stream. So, but the budget to count the atom are small. So
what do you mean the budget of counting items?
So assume there are 100 different atoms, but we only have 10. We only have 10 bucket to count. We only have 10 counter to count them. So how to guarantee that we can get the approximation of the counting well.
So if you need to count 100 different items and you only have 10 counters, is that what you're saying?
Yes. So the result is that it will trying to count the top. So if we have 10 budget, it will trying to count the top 10.
Okay, so the
10 atom. Yeah.
The point is to get the most frequent items.
Yes.
Okay, that's much more clear.
Okay. Yeah. So So that's the goal of this algorithm. But in practice, maybe it will not to get the exact top k. There can be, I mean, it's not for this algorithm. It will, so maybe for some atom which get some low frequency can also appear in the final result. So it will assume with the atom which not appear in the counter, the counting of the number would be 0. Yeah, is this algorithm clear?
What's the trick here? What's the says if the size of k is bigger than 1 over eta.
Yeah. So actually the epsilon here is the error. So we can look at the guarantee of this method. So the Gj is the estimated frequency, and Fj is the ground truth frequency. So it can guarantee that their difference is smaller than m divided d divided l. L is the budget. So
so what's the goal? The goal is to approximate frequency or find the most frequent items.
I think the goal is to approximate the frequency for the most frequent items.
Yeah,
Okay.
because actually there is a budget, so it will try to only keep the most frequency item.
What's the relationship between L and K? Are they the same thing?
The L and what?
The big K.
Oh, L is the K here, because actually I got them from 2 different papers, so their notation is different. K is the length of K is equal to L.
So it's saying that if we want to, so assume K is 10. So if we want to get the frequencies of the top 10 frequent items, then use this algorithm, we can guarantee that the frequency, the error will be less than n divided by k.
Yes, because so you can assume that because every so here actually yeah, so you can think about that. So because it will empirically delete the subtract the counting by -1. So we can think about what if there is one atom in every time it deleted it tries to subtract the counting by 1. That atom is always in the K. So it will at most being deleted by n divided L times. So that's the most difference between the estimated frequency and the actual frequency. Is that clear for you? Okay, so
it's a very important part for your presentation. I think we don't need to like prove that our is correct. We believe it should be correct.
Yeah. So the yeah, I think we can just get the basic idea here, and because because the frequent for the frequent direction, it works on the matrix. The detail are different, but the basic idea are similar. It tries to preserve the highest frequency terms. Yeah. Okay. So, all right, we can go to the. All right. So actually, on this slide, it tries to give out some it tries to extend to the matrix. So assume A is a matrix, and the streaming is that it will give out the rows of the A one by one, and for to make it simple, we just assume that for the rows of the matrix, they are the basis vector from E1 to EM, and now we need to calculate the frequency of the EI in this streaming. So we can know that for the so for the frequency of the EJ, it would be equal to A multiply EJ and calculate its spectral norm, or just the norm, right? Because the EJ are basic vector, they are orthogonal. So when I multiply A with the EJ, their norm would be equal to the frequency of the EJ. Is this clear?
What are they trying to do here? Like in previous setting, we say we will have 100 items, then will appear several times. Here, what do we assume about the matrix? I mean, every row of the matrix could be different. They are real values.
Yeah.
So what do you mean by frequency?
There is a pool of the AI. So in that pool, there is only m vectors. The number of the unique row would be m.
So there will be several row vectors that appear several times.
Yeah. They need to calculate the frequency of each row, not the of each basis vector.
I see.
Yeah, because the basic vectors are orthogonal. So when we calculate the frequency of one vector EJ, so it would be A multiply EJ and calculates norm, right? Okay, so so if we still also apply the frequent item, like and we can apply the bound from the last slide. So and we're extend to the matrix So we will get some bound like this. So this is a very simple extension about how to how to extend the frequent item into the matrix. So it means that if we just have a matrix consist of the basis vector, and we want to know we want to know the top m, not the top k or top l, most of frequency vector, then we can estimate, we can approximate A in a smaller matrix. So that's the intuition here. But as we know, it's hard for a matrix to be consisted of the basis vector. So this is just a very toy example to get the basic idea here. Is there any problem here? Okay. Then we will introduce the frequent direction method. So for arbitrary matrix, the dimension is n by m. And also we want to process its rows one by one, and tries to produce a sketch matrix B. So the dimension for B is L by M, and L is much smaller than N. So the general idea for the frequent direction is like the frequent atom. It will try to get out the most dominant directions in the matrix A and its corresponding singular value of A, and use that to approximate A. So it's similar like the SVD, but it will try to calculate the singular value and the singular vectors in a streaming way.
So here we want to reduce the number of rows of the matrix A, right? So from N to L.
Yes.
But in the beginning you said we want to. The problem is D is too large. We want to reduce the size of D.
Yeah, you can. I mean, for my original problem, you can just have a transpose of the gradient. Then it will the same as the matrix scale, right? I mean,
no, you will change the meaning of the problem. So if each row is a data point, then here this algorithm essentially will reduce the data points but keep all the feature vectors. It is different from reduce the number of features, which we normally do through like PCA.
Yes, I mean, if I just have a transpose on the gradient, then it's the same as the A here, right?
Gradient is a vector. Here it's a matrix.
Sorry. The gradient for single input is a vector, and but in this method actually it needed to accumulate data point, so that when if we calculate with the matrix way, then G would be a matrix.
So let's go back what you're talking about right now.
So I think
Okay, what's the idea? What's the idea to find such a sketch matrix B?
Yeah, so the basic idea here is that it's trying to every time it's trying to get a block from A and calculate its dominate singular value and the singular vector, and then finally use that to represent the original matrix. And so what Zhimeng just asked is about the dimension. Actually, that's a, I mean, we can have a very simple trick to solve that, right? So the basic idea for the frequent direction is that actually the direction here means the singular vector. So the frequent direction, it means that it will try to figure out the singular vector with the highest singular value in the matrix A, but it doesn't use the SVD. It will be calculated in a streaming way, and at the meantime, it will give out some guarantee to show that its approximation is within some error.
Show me, you have a way
within some threshold. Yeah.
Single value of A, maximum single value of A.
Yes.
And with
That's
this value, what do you need to construct B?
Yeah. So maybe we can just look at the algorithm directly. So in this algorithm, it firstly it have a empty B, and then it will fill the rows of A one by one into B. And when B when B is full, then it will apply the SVD on the B, and it will calculate its singular value and the singular vectors. And then so assume here we have its single. We will have the sigma, the matrix here, and we have a sigma 1, sigma 2, and until we have the sigma like L divided 2, and the last one is the sigma L. And what it did is that it will pick up the value sigma L divided 2, and then it will with sigma 1 square multiply sigma L divided 2 square, and have their root to add a new sigma 1. It will do like this for all the.
Which line of the code is doing what you said here.
Yeah,
What I said, the
yeah.
sigma theta.
Yeah, in this one.
Oh, the big sigma is a diagonal matrix.
Yes.
It's horrible notation. Okay. It's if you take square is subtracted by the maximum of no, it's not maximum. It's just
Yeah, it will subtract the singular value in the middle. So if we rank them, so and then because there is a max matrix, then for the remaining singular value, they will go to 0.
okay.
Yeah, so it's somehow like the frequent atom algorithm. When it calculates the frequency, it will always try to subtract the frequency.
So I mean the singular values represent the frequencies, the frequency of the directions.
Yeah, actually here I think that's a norm. That's a norm of the direction. It will shrink or direction by the same amount.
I think the frequency directions are actually the singular vectors here.
Yes, you are right. Yeah, that's
half of the frequency, half the lower frequencies.
Yes, you're right. So the benefit is that every time when we calculate the singular value and the singular vectors, when the norm of one direction is small, it will become 0 with the max function. So then it will always remain the singular vector of the house, the singular value, right?
Yeah, but okay, but if you do the singular SVD over A, the singular vectors are not necessarily the same as the singular vectors in B.
Yes, you are right. So actually, for this algorithm, it has a loop for the outer loop. So every time when it only keep half of the singular value, it will fill in another two L divided 2 new rows from the A. So it will keep update the singular values and the singular vectors, and makes it to approximate the real dominate singular vectors.
Okay.
Yeah. So is there any problem here? All right. So then actually from now we are going to go to this paper. So actually for frequent direction is a that method to calculate the sketch of a matrix proposed in some previous paper, and in this paper it used this method to solve the problem, the rigid regression problem, as we had shown in the beginning. So in this solution of the rigid regression, we have those terms, and in this paper it uses the frequent direction to calculate them, and it can guarantee that the relative error the relative error is about the epsilon, and with this it only need about 1 divided epsilon rows. So that's the rows for B in the Prowess
B will be L by N, right?
L by D.
It says use frequency directions to estimate A transpose A, not A.
It's used in A.
Or it just
yeah.
tries to estimate, to find a B to approximate A.
Yes.
Okay, then that is not estimate A transpose A, it's just to estimate A.
Oh yeah. So yeah. So and because but in this paper, because as we know, when we calculate the when we did the SVD on B, actually we can
B transpose B, but it's okay. We just need to know what's the B represent for.
Okay, all right. So for this problem, the running time is ND and multiply L. So this would we need to, I mean, this would be much smaller than the Prowess method.
What's
would
this
be ND square.
This running time for what? For calculate the solution of X, a solution for B, or what do they call it? X. Okay. X.
Actually, the time here is for this term, for the inverse term. Because in this paper, it tries to use the frequent direction for the rigid regression problem. So the most time-consuming operation in this is to calculate the inverse, and when it's calculated the inverse, firstly it used the frequent direction to estimate A, and the overall running time is O and DL, and in the Wood-Fisher paper, the time is N multiply D square.
So you mean when they get B and they just plug in B and use the Wood-Barrow formula?
No. Of course not. I'm just trying to compare the time consuming with the Wood-Fisher.
Calculate inverse is OD3, right? OD cubic. The matrix is D by D, and calculate inverse of it is D cubic.
Yeah, I think it
come from.
Yeah, so it's so if we have a matrix and calculate its inverse directly, so the time consuming would be ND square, OD square.
Yeah.
And here, because we it used the Wood-Barrow method to calculate the Hessian inverse. So firstly, it approximates the Hessian with a matrix of the gradient G So it would be G transpose multiply G and then get the mean.
Why MD square is better than D cubic? I don't understand. Assume M is larger than D.
Yeah, so there is a trick in the Wood-Fisher paper. It uses a very small subsample of the it use a very small subsample of the data. So assume for the whole training data, maybe we can have 50,000 training data, but when we calculate the Hessian inverse, we just use 5,000.
And the number is much smaller than D. Otherwise, it makes sense.
Yes, but it will if it will somehow may affect its performance, right? We don't know. I mean, in the Wood-Fisher paper, it says that it can use a small subset to sample the gradient, and the performance doesn't change much.
Okay, can go to your current.
But it cannot guarantee.
Can go to current slide, the most recent one. So the running time is MDL, and original ones like DDD. So they assume M multiply L will be much smaller than D square.
Yes, the L is much smaller than D.
And M is much larger than D. So ML should be, how do they measure this value? I mean, we should have ML much smaller than D square. Otherwise, this algorithm won't make sense, right?
And we need to have an L smaller than ND. So for this one is the NDL. We just need to guarantee this, right?
But you directly calculate the inverse here will cost you MD cubic.
No, for this method we don't need to calculate the inverse, because when if we have the SVD for A, and then we also know that the singular value of A transpose multiply A, and also the corresponding singular vectors, and with them, because the second term for the I,
we can. Okay, Xin, you are talking about a lot of irrelevant things. We need to know that once you get this B, how do you get inverse? Right?
Yeah.
It's the key thing. Otherwise, if you run a better formula again, what's the meaning?
Yeah, I mean, if K is L by D, and then the B transpose B is also D by D, then you do the inverse. It's the same complexity.
I think after the algorithm, we have the SVD singular value decomposition for B, so we can use that form to calculate the inverse.
Yeah, so we can have something like this, right? And for I think we with this we can have the then for this term we can have something like this. and with for the I, we know it's equal to
just VV transpose.
yeah, I think I have
Just adds up
VV.
gamma to the eigenvalue.
Yeah, so we can for those two terms, we can finally to make it to be something like the V inverse, but we know the V inverse is the V transpose, and then gamma, something like this. I think maybe it's not exactly correct.
But
Yeah,
when you start computation,
so with this, we don't need to calculate the inverse.
and in their calculation, how does they calculate A transpose B? Is it still calculate the original A transpose B, or they also use B to replace A to do this?
They use B. They also use B. So because
Okay.
yeah. So with it means that most of the time consuming step in this method would be use the frequent direction to calculate A, and after we get the decomposition of A, we can get the inverse of the first term easily, and also we can calculate the second term easily, right? So
yeah, that's very interesting. That's very interesting. Perhaps it's it will be better than just the random estimate of the hash rate.
yes. So we can check the algorithm here. Actually, there are some in this part. Okay. So, wait for 1 moment. Yeah. So in this part, actually, that's the frequent direction in we have introduced previously, and the difference is that it will have those two lines for how to calculate the terms in the solution, and we can check the do you have any question? Okay, so we can okay.
So in the line above return, so after they calculate the decomposition, and the inverse will become the just divide the diagonal element of the eigenvector, right?
Yeah.
Okay.
Yeah. So that would be easy to calculate. Yeah. So in the next, we can check the space and the timing for this algorithm. So because every time we just need to so I would like to say in this algorithm the notation is somehow different from the previous paper, but I mean it's the same. So here it calculates the C, and C actually that's the that's the eigenvalues matrix multiply the right eigenvector, and then it will append the new rows of A after that, and then apply the SVD. So here the yeah. So here actually the dimension of this matrix we apply with SVD is 2L multiplied D. That's the difference from the previous paper. So with this one, we can say that for the space actually that's the 2L by D for this streaming algorithm, and the running time is that if it will have the for each step in the loop, for the out loop we have n divide L steps, and for each step for each step inside, actually that's the running time. So finally that's the NDL.
So every time they sample a batch.
Yes.
Okay.
Yes. So they just pick up L rows sequentially.
Oh, so they just do the sequential.
Yes, this is a streaming algorithm. Yeah, they were not repeat to, and I mean they were not pick up a row again.
So in the second last line in the algorithm table, the X hat gamma is the prediction, isn't it?
Yes. So that's the estimation. So on the right, so
It's the
we can.
result. No, you don't need to show the detail. I just want to confirm.
Yeah.
Is the just the trick you said, like applying the eigen decomposition form and plugging to get the ridge regression prediction, right?
Yes.
Okay.
All right. Is there any other problem?
So what they are doing is essentially calculate a new set of, like a new format or a new collection of data points.
A new collection. You mean how to generate to some new data point?
Is this method applicable to other like a regression problem, not linear regression, but other types of problem?
I don't think so. Yeah,
Why?
I think
it only makes sense for linear regression.
Actually, could you give me an example? What other regression problem like?
So they use a B to represent A.
Yeah.
And that B is essentially a new representation of the data set.
Yes.
So they finally give the weight of the linear regression. It's just using a streaming weight to estimate the weight of the ridge linear regression.
Okay, so B is only intermediate, it's not the goal.
Yes.
B is not intermediate. B is just the response, the Y.
I mean the
A is the training set. Like you have a huge training set A, and the B is your Y. You can view A as X and B as Y. And you know that if you run ridge linear regression, then the optimal weights will be A transpose A plus gamma I inverse A transpose B.
I think I mean
Yeah.
the big C, not the B.
C is the intermediate result.
Yes, C.
Yeah, and then
C.
there are X hat Y is essentially the weights, the learned weights of the linear regression.
Yes, C is like the new representation of the data set or the streaming data set.
I agree.
You mean big C or small C?
Big C.
Yeah, big C should be the big C should be the big B, right?
Yeah.
That's
Yeah,
what
so-
I talk about B.
Yeah, actually, I think I didn't actually I didn't understand SVD well. So my question, I have one question here. So when we use the SV calculate the SVD, we always get the left singular vector. Why we can recover the C, we only use the singular matrix and the singular vector, right singular vector. Why we don't use the left one?
Because they only want to maintain the property of the row space.
Okay.
Because for each, we are trying to count the most frequent row direction. So that's why they only use the right matrix.
Yeah, I for that I understand that. Actually, what I'm
So C, this the last line is the last line is essentially after the streaming process, right?
yes.
So it's like they transform A to the some M by D matrix to L by D. The last line is simply estimate the regression coefficient. So if we want to do nonlinear regression over C, we can just stop here and do whatever following. Like for example, we apply a GP here or neural network here using the streaming data sets.
You can, but the problem is how do you make sure the parameters? Here is just estimate the weights of the bases. If the neural network, you also need to identify the parameters of those bases.
But this parameter is based on the final data set C. It's totally determined by the final C.
Oh, you mean when you get C, you just use that to train your neural network?
Yeah.
Yeah, probably.
That's another way to do the streaming regression problem.
You're doing streaming sketch of the data set, and then you use that data set sketch to train the model.
Yeah.
Right?
Yeah.
Yeah, I'm also curious, do they have like a kernel bridge regression version, I mean, for this? Did Benwei discuss with you about that?
The kernel.
Yeah.
No. What? How to do that? Could you have some simple description for that?
Okay, never mind. because kernel ridge regression has a very similar structure like this. You just
Okay,
replace
okay.
A transpose A by a kernel matrix on A. So if you get B, you get kernel matrix on B, and it's kind of like computation is almost same, except that you're gonna first do a apply the kernel function of that, and then do SVD. I'm not sure if you do it in a kernel space, you can assume that D input dimension D is infinite dimensional, but it's reduced the row of the row space. It should be fine.
Okay.
Yeah, so here they also said that the final solution is simply determined by C.
It's not just determined by C, right?
It is determined by C. So this is to get the weights, the linear regression,
okay.
of linear regression.
It's regret on C.
Yeah, you are talking. Okay, you're talking about the capital C. Okay.
Okay. Well, what else are left?
Yeah. So then there is an illustration about the distribution of the singular value. So the y-axis is a square, and the x-axis is the index of the singular value, and it has already ranked the singular value from the large one to the smallest one, and here the black line indicates the real singular value of the original matrix, and the blue one means that it adds a range, and so there is also two lines with the bound. So that's the bound provided in this paper, and the lines without the bound, this is just the illustration. So it has shown that the empirical singular values between the real singular value and the bound. So the bound is tight, and it will push the solution close to the real value. Is there any question here? And there is also one with ridge and without ridge. So we can say that if we just look at the real real singular values of the original matrix, we can say there is some gap between that. That's because in this solution we have this term, the gamma I. That term brings the value gamma here, and it will bring some difference in the singular values. Any question here? Okay, and then, yeah, actually in this paper, it also provides some analysis of the error. So for this error, firstly it defines the coefficient error. So for the coefficient error, that would be the x gamma hat multiply x gamma, calculate their norm, and then normalize that. that's the relative error. It's called the coefficient error. So it will evaluate how well of this FD algorithm performed, and also it provide another two term. The first one is the Bayes error. The second one is the variance error. There have some complex formulation about how to calculate them, how to get the bound. I didn't understand very well of the detail. And
what's the bound of the coefficient error?
The bound of the coefficient error. So, yeah, it would be something like this. Something like this. Yeah, this is the bound for the coefficient error. So the hyperparameter would be L. L is the dimension of the B. B is L by D, and the gamma here is the coefficient for the regularization, and the sigma is the coefficient error. I didn't know what's the K here.
What does AK mean?
Oh yeah, I remember that. So for AK, okay. So as we know that, so for a matrix we can for matrix we if we want to keep the top K singular value, we can use that to approximate A. So AK corresponding to the matrix recovered by the top K singular value and its corresponding singular vectors. So here what we get the B is only tried to approximate AK.
Okay.
Yeah.
Okay. Yeah. Let's skip this. This is not useful for us.
Yeah. So, any question here?
How will this algorithm help for calculating the inverse Hessian?
Yeah, so firstly, like in this algorithm, we can we only need to it's somehow like this when we calculate the Hessian inverse, actually it's the G transpose multiply G and calculate its inverse. This formulation is like this, right? So we can just use this algorithm to calculate the Hessian inverse, but we don't need the last two step.
And GT is the gradient vector of every data point?
Yeah, it's M by D.
Oh, okay. This, I think you were better write as a approximation.
Yeah. It's a approximation. It's from the Wood-Fisher matrix.
It will make it more efficient, but I mean, in your problem, is this efficiency a critical point, or the performance, final performance is more critical point? Essentially, from M to small l, but in Wood-Fisher, you mentioned the M is already very, very small.
Yes. So so actually, because in Wood-Fisher, it only uses a small m. So it in that paper, it didn't provide any guarantee of the performance. And for this method, actually it's very fast. I would like to say, so if you check this result, so actually the data size is also very large. When L is equal to 2 over 12, I think it's about 1 million, right? I think it's about 1 million, and with the large data point, so it can be finished in. So here you can say that it maybe just spend more than 10 seconds, and in the Wood-Fisher paper, actually it can take maybe half an hour.
No. What's the number of the data point? 1 million?
2
to the 12 is not 1 million. 2 to 12 is like 4,000.
4,000. Okay.
With 210 is 210 is 1,000.
Yeah. Yeah, so okay, yeah. Then I needed to check what's the time consuming if it increase 1,000 times.
Yeah, like for 1 million, this level in deep learning application you're working on, maybe it's not faster than Wood-Fisher's algorithm. But maybe the good thing is they have a time bound.
Yeah, so because actually the time is NDL, so I think L is also important. How to choose that. So I discussed how to decide the L with Benwei, and so he suggests the L is close to the empirical rank of the matrix. I feel yeah, I think I need to check something like this figure. Maybe I can calculate all the singular values and check the empirical rank for that matrix. So if the L is much smaller, I think it will also reduce the running time dramatically. Yeah, that's a presentation today. Do you have any question for this one?
Question? I think in addition to time complexity, I think more appealing thing about this is they have some explicit bound on the error. That might be more accurate than the right now the way to compute the hashing. approximate hashing because it's just a simple simple estimation with stochastic estimation of that. So that's something I feel it might be promising. But of course, you need to check about the time complexity as well.
Okay. Yeah. Yeah, I will do that.
Okay, thanks. I think from next week, we're gonna temporarily stop the seminar because there will be around 2 months before the deadline of NeuralNIPS. I hope everyone is focusing on the paper submission, and also we're gonna use 1 week, I think 6 days, focusing on the rebuttal. So let's temporarily halt this seminar and then focus on research. If we really need someone to present something new, we can do a few like temporal or casual seminars in the remaining of this semester. Okay, thanks everyone. Have a great weekend.
Thank you.
Thank you.